different keys, is there a written description? Like, can I read it? Like, is there a text I can read? Because like I totally forgot.
I can write that, yeah. This is the design of our first rocket. So you had an idea of what the design team is going to do, but you did not know about what avionics team is going to do. So this is gonna be our avionics bay. Right now, I'll show you my screen in Fusion 360. So this is the current model of our level 1 high power rocket. I can dissect this, sectional analysis, to see inside. So right now, as you can see, this is the PCB. There's just one single chip right now. It's an accelerometer. We want so many things to be done by our avionics bay, like our flight computer, but just one chip cannot do everything. So we're gonna have chips for each task that we want. We have to think about it, and we have to make a design of this computer. So let's begin today's meeting. I'm gonna teach you about signals, about how do you work on those signals, how do you make your own computer from a bare chip, like an STM32 or an Atmega 328P. So let's begin. In the winter break, I gave 8 lectures on rocket science and all these things, but there were not many people as there are now. So I'm gonna walk you through those slides. So there's something called schematics, or let's just start with the signals first. Okay. I'm gonna turn the lights on. Does anyone have any idea of what signals are? How would you define a signal?
Like something that's like sent out. Maybe I don't know like what the thing is, but just like something that's sent out.
Pulse.
Pulse? Pulse is a signal. Pulse is an example of a signal. But what is a signal? Yeah, that is also an example of a signal.
I would say it's like a low-level thing of like communication from one part to the other. Like whenever I learned about signals, it was like in operating systems. So it'd usually be on like some hardware stuff. I don't know.
Yeah, you're close. It is actually a low-level thing that is used for communication. So, signal is something that can transfer data from one place to another. So, if you wanna, let's say, transmit your data from position A to position B, then you have to generate a signal from that A location, such that the signal is gonna travel, and whatever signal you're using, like there's something called a carrier that carries your signal. So right now I'm speaking, right? So how is the information going from from me to all of those people, all of you guys? So when I'm speaking, my vocal cords are vibrating the air molecules. They are generating pressure waves. So like high pressure regions and low pressure regions in air that are traveling in the air. Air is a medium, air is the carrier of this signal. and then that's reaching your ears, and you're listening to it, and your eardrum is again vibrating according to those pressure waves, and then that's encoded in your brain, and you understand that. So we want something like this for anything or everything that we wanna uh, implement in our side computer. Let's say we wanna know our location, the location of our rocket. So we wanna generate such a signal that can be transmitted over electrical, like over electricity, like a voltage signal, because that's what our computers understand. Our computers understand voltages. So we want to convert our position in such a way, like we want to encode that information in voltages such that it could be interpreted. So how can we do that? So also signals could be like of two types. It could be, especially for electrical signals, they could be of two types. It could be like this. This is called a binary signal or a digital signal. Or this could be like a sine wave with changing amplitudes, with changing frequency and changing amplitudes. So we can encode our information in a signal looking like this, as well as in a signal looking like this. So in computer science, we call this one or true or high, and we call this state zero or false or low. This is a digital signal, and this is called analog signal. I'll give you an example. Do you guys know what a resistor is, or what a voltage is? When I say 1 volt, what does that mean? Is there anyone who does not know? Because I can give you like a quick walkthrough of electronics. So there are a couple of devices in electronics. Like one of the most commonly used devices, a resistor. This is the schematic symbol of the resistor. This is how we just represent that on a diagram. And there is something called inductor. This is how we represent an inductor. And there is something called capacitor. Capacitor looks like this. They have different functionalities. So when we generate some current, let's say, so what is a current? Let's say this is a loop of conducting wire. Let's say this is a loop of copper. So when I say that there is some current inside it, what does that mean?
Those electrons.
Yeah, electrons are flowing, right? So there are charges flowing in this wire. Let's say charges are flowing in this wire right now, and we look after 1 second, they're not flowing anymore. Because there's something needed to be, to make them keep flowing. They're gonna stop by themselves because they have collisions internally, and they're gonna stop. So we add a battery in a circuit, we break the circuit, we add battery inside it. The schematic symbol for the battery looks something like this. This is called positive voltage, positive side of the battery, and this is the negative side of the battery. There have to be some potential difference between these two terminals in order to keep the electrons flowing. These are electrons, by the way. electrons goes from negative to positive, and in our convention we say that the current is flowing from positive to negative, because we say that the current is the flow of positive charges. So, but electrons are negative, so they have different directions. So the current, I can draw that with the green pen or the purple one. We represent current by I. So current is flowing clockwise, and the electrons are flowing counterclockwise in the circuit. This is just a weird convention that we say that current is movement of the positive charges, but there are no positive charges that are moving. There are electrons that are moving, so we say that they're opposite. So this is a resistor. We represent this by R. This is inductor, I or L, inductance, and this is capacitor. We say that its capacity or capacitance is C. Now we can make some circuits, and we can play with these signals using these circuits. Let's say you connected. Let's say you are using this plug here. So there is some signal that is coming in that plug that is powering your laptop. That signal is going to look something like this. If you so this, on y-axis it is voltage, and on x-axis it is time. So as time goes on, your voltage is going back and forth between some positive and some negative value. This is the signal that is coming from the power plug on the wall. If you cannot use this to power your computer, so something is happening inside it that you're playing with this signal. This signal is getting modified, and then it is powering your devices. So what's happening is there's something called a rectifier that is rectifying this signal. What does that mean now? That means like all of the negative parts of this graph are flipped along x-axis, and they are mirrored. So every wave is like totally positive. This is called AC current. That is alternating between positive and negative. This is called a DC current, whose voltage is always positive, is never negative. Now, even if you use this, voltage is going to harm your devices because this is changing violently. So what can you do about this? So what we do is like, let's say, that this is the wall output, and let's say this is plus and this is negative, and then you attach your device with this. You want to attach your device, then you need to charge. It could be your laptop or something. So you will not attach it directly. You will add a rectifier first. I'm representing the rectifier like this right now. Now the signal here is, but even this signal is going to harm your computer. So you have to put some other devices in between so that a clean signal looking like this goes into your systems, in your laptop, for example. So what is that other device that you can add? One is capacitor. You can add capacitor here, and you can connect this to the ground, to the negative again. What this is going to do is, so I'll tell you first what a capacitor is. If you're going to apply some voltage difference across a capacitor, then it is going to create some charge on that capacitor. This plate is going to be having positive charges, and this plate is going to have some negative charges. And the current cannot flow through a capacitor, a DC current looking like this cannot flow through capacitor because it is a literally like they are spatially separated. So how is the current going to flow? It doesn't flow through air. So this basically stores charge. So we use capacitors to store charges. And this comes handy in situations like these. So what this is going to do is it's going to store positive charges on this plate and negative charges on this plate. So right now the signal in this wire looks like this, but as soon as we added this capacitor, what this is going to do is, I'll draw here. The voltage is increasing first, the capacitor gets charged. Now as soon as the voltage will start to drop, we want it to drop like this, but because there's a capacitor in the circuit, this capacitor has some charge stored inside it. As soon as the voltage will begin to drop, this capacitor will start dumping its stored charge inside the circuit again, back again. It's gonna look like this. Then the voltage will again increase. And as soon as, like now the capacitor is charged again, it's going to dump its charge again. So you smoothen the noise out like that. So capacitor is like dumping charge when it's required in the circuit. Then, but still, this is still not enough to charge your computers, your batteries. It's still gonna harm your computer. So there's some other steps that we add. One of them is called a voltage regulator. It is gonna look something like this. So this is very close to what we want in our systems. Now, if you zoom into it, if you scale the x-axis, like if you zoom in the y-axis, you're gonna see that it is very bumpy on micro scales. So you can even remove these noise. So this noise has some high frequencies inside it. So if you apply a low pass filter, what a low pass filter does is it can take in a signal like this. And it's going to cut all of the frequencies that are pretty high. It only allows low frequencies to pass through. So this, after filtering it through the low pass filter, is going to look something like this. Now, the higher frequencies that are like that are cut off. There are only very low frequency variations in the voltage now. So this is what we can use to power our computers. So this is all the circuitry that goes inside your laptops to power it up. Now, when we make our flat computer, we are not using a power wall like this. So we're not dealing with this kind of signal, but we are dealing something more like this. So let's begin making our computer. If anyone have any questions or want me to repeat something, you can. Yeah. You want to take a picture? You can. Otherwise, I'll upload the lecture. It's recording.
It's kind of intimidating when you learn this for the first time, but like once you start making these circuits, once you start working in the avionics, you're gonna get used to it, and this will feel like pretty natural to you. It'll come like an intuition to you. So let's start the rest of the meeting. Let's design a computer for this avionics bay right here. Let's try to implement one of the functions that we're going to need in our flight computer. If you have opened Fusion360, click on File and New Electronics Design. Then you can close this data panel. And here you should see New Schematic, the leftmost button. If you open that, you will see this intimidating looking window. So to begin with, I'll tell you what a schematic is. So the way we design things in electronics is there's something called schematic. I can show you slides. This is how you draw circuit diagrams. And if you will extend this idea all the way, then circuit diagrams could be pretty complicated. We call these schematics. These are transistors. You can make logic gates using these transistors, different logic gates, XOR gate, OR gate, NOR, NAND. And these are a couple of definitions: transducers, sensors, actuators. So I told you what a sensor is. Sensor senses the physical environment and it encodes that into a signal so that it could be interpreted or transmitted later. And receiver or transceivers is basically the thing that receives or generates those signals to propagate them through any medium. And actuators, on the other hand, they're like, say for example, you are controlling a robot. So we call actuators for things like motors, or if you have any hydraulic pumps or something, that can make a physical thing move or some motion in real life, in physical life. I'm not going to go through these slides. These are my winter break lecture slides. If someone's interested, I can share the link. These are a couple of sensors. So this is the chip, the computer that we're talking about all the time. We're gonna use this to make our flight computers. We can connect a bunch of sensors to this, and the way we connect a sensor to a chip is called communication protocols. So the industry has standardized some protocols that they're gonna use to communicate back and forth, so that the manufacturer of the chip knows how to design these pins, and the same protocols are gonna be used by the company or the manufacturer that's going to manufacture the sensors, so that they're compatible to each other. So if we also understand those communication protocols, then we can implement them and make whatever we want. in the Fusion 360, now let's import some of the libraries here. So if you go here, place components,
Do we
click on
go on, sorry, do we create a design?
create an electronics design.
Uh,
Then there should be a new schematic button.
Okay,
Got it?
a new schematic then?
Yeah, new schematic. On top left, there should be some here.
Oh yeah, I see.
Yeah, click on that, you will come to this window.
Or I see.
Now click on this place components. You will be able to see all the components here. You can search for whatever component you need. Search for STM32. You will see a bunch of options. If someone does not see any option, then let me know, because there are many things that you have to go here and search for the libraries. You have to import those libraries, then those components are going to show up. So if you don't see anything that I see on my screen, then let me know.
Yeah, I only have two.
You have two? Because I have this additional library. Let's just go with this one, the second one. Double click on it, and then you should be able to place this in your schematic area. Just single click on it, and it is now placed. It's gonna stick to your cursor still, and you can like place multiple copies of it. But if you hit escape key, then it's gonna go from your cursor. Now, this is the chip. This is the simplistic version of the chip that we just saw. So in schematic, there's a simplistic diagram of the original thing. It's called symbol of that diagram of that component. Now let's add some resistors. Search for a resistor, and you're gonna see this. There's a drop down on next to the resistor. So if you click on that, you will be able to see different types of resistors. So which one to use now? Now in PCB designing, there are two types of components. We classify them into different types. Turn the lights on. So a PCB is nothing but a printed circuit board. So whatever we talked about like this, we add more components in it. We place those components on a board. It's called PCB. Printed. It is nothing but a layer of bunch of layers stacked on top of each other. This is copper. Okay, this is insulator. And these are copper pads on top of the insulator layers. And if you'll see this from the top, in our avionics, this is one of the schematic that I made. It's gonna look something like this. Then we wire them, we route the wires, and it's gonna look like this in physical life, in real life. If you'll see, these are the copper traces, these lines drawn on the board. If you look at it from the top, we deposited some copper in a particular design. Let's say this is copper that I'm drawing.
let's say there's an LED here. And let's say there is a resistor here in this circuit. So I can trace these copper paths and then I can connect battery here. Now we draw these copper paths. That is called PCB designing. So we have these components, we have the board, we design these copper paths, and then we get it manufactured from a manufacturer, or we can print these copper paths by ourselves. There are different methods to do that. We can discuss that later if we get the time. And so I was telling about two different types of components. So this type of component that I draw here, a small LED and a small resistor, is called SMD, surface mounted device. They're pretty smaller, they're pretty compact, and you mount them on the PCB. They do not pierce through the PCB. But there are other type. The other type was right here in the Fusion360 in the drop down list. So this type of resistor is gonna pierce through. You have to have a hole in your PCB all the way. And then the resistor that's on the screen right now, this one is going to pierce through these holes. And then you solder these legs from the other side. So type 1, we can call it like clunky or something. It doesn't have any name. And then we can call this surface mounted devices, SMD. So right now let's pick a non-clunky SMD version of this resistor. So double click on this. Then you should be able to place this in your schematic. Let's place a bunch of them. Done.
Doesn't matter which one we pick as long as it's not the one we have to solder, the one that goes through.
It doesn't really matter, but in flight computers it does.
Oh, okay. So this is just like practice.
Yeah, we're just like taking a walkthrough of the software.
Oh,
Now let's add an LED. Let's go with this one, LED chip. We can go with any of these, because here you can see the 3D package for this. So there's a 3D model attached that how does that LED looks like in real life. You can see that here. Let's go with any of these. Let's pick a red one. Double click on it, and then you should be able to place this in your schematic. When you're placing any component in your schematic, if you'll do a left click, if you do a left click, it's gonna rotate. So you can rotate it if you want. And then hit escape, and then let's add some capacitors. Again, capacitors are of these types. These are the bigger ones that's gonna pierce through your PCB.
and these are the SMD ones. Let's take any SMD one. Double click on this capacitor, then you should be able to place this in your schematic. Let's place a couple of them. Then hit escape. And also don't forget to save this project by hitting Control S or Command S if you're in MacBook. Name it Meeting 4 or something.
Sorry, how do you check if they're the CND ones? At least the
SMD ones?
SMD.
You can drop it down from here, and then these are the smaller, like the surface mounted devices. But this kind of capacitor is the clunky one that, like, you must have seen this capacitor in the circuits,
Oh yeah, yeah.
right? This pierced through your PCB.
Oh, okay. So just ignore those ones. But
Yeah, as of now. Once everyone has done this, let me know and then we'll move forward. Should we move? Okay, let's go. Now, to power this up, you again need a pretty steady voltage. You can use a battery, but the battery is gonna produce a noisy signal, just like it was here. It's not visible anymore. So to deal with that noisy signal, we are gonna use these capacitors. And the way we do this is, so there are so many pins in this microcontroller. These pins VSS, they are for negative terminal or the ground terminal, and the pins on the top VDD are for positive terminal. Let's also from the libraries, let's also place another component, VCC. If you're gonna search for VCC, you will find this. Double click on it and then place it in your circuit. Hit OK. And also add GND, that is the ground terminal. Should be right here, something like this. Double click on it and then place it in your schematic. Hit OK. Escape. So this is your positive terminal and this is your negative terminal. Now you can connect your positive terminal directly, but that's gonna cook your STM32 microcontroller. So what we're gonna do is we'll first add some capacitance. Just follow me. What I'm doing right now is all gonna make sense in a while. So draw this connector like this. Bring it here, and then also connect these pins to the same. Then you can click on the select thing and then select your GND, move it all the way down because the negative pins are here. or the ground pins. We are also going to connect this. Now you kind of powered your STM32, but the power signal is not clean yet. We're going to fix that.
Sorry, how do you move the ground to the corner?
Click on this select tool on top right, and then just drag it.
Oh, okay.
Yeah. I'm gonna save it again. Did everyone do this? Okay. Now, let's add some capacitance in here. Just like we saw, it's gonna smoothen your voltage. Drag and bring your capacitor near this line. You can rotate this. Done. And then click on this group thing. Move this group all the way down here. Now connect these capacitors to this line. And just to notice, there are four pins for voltage here. So we're gonna add 4 capacitors, one for each pin. And the other end of this capacitor is gonna go in the ground. So I'm gonna copy this ground thing, this ground pin here. Control C, then Control V. What happened? Control C, Control V. I'm gonna place this here with a bit of rotation. And then I'm gonna connect this to all of the capacitors. Gonna save it again. If anyone is facing any trouble, then let me know, I'll help.
So do we need another ground? Do you have like 2 grounds? Oh, okay. Just
You can put multiple grounds. It's the same thing though.
oh, okay.
Yeah. Are you all done? Now we're gonna add capacitance values to all of these capacitors. If you'll right click on this, you will be able to see value here. You can say 100 microfarad, or wait, give me a second. Attribute.
So you use like U?
Hmm?
You use the letter U?
Yeah, I use the Eagle PCB instead of Fusion360 Electronics, so it's kind of new for me.
Oh.
But that's almost the same, but a couple of things are different. You should be able to click here, Design Management, Manager tab. All your components are here that are in your schematic, and then you can change the capacitance values, or so yeah, it's right here. So you can okay, so you can say that, okay, yeah, it's values right here. So you can add, let's say, 100 microfarad, okay, and then in the C2 you can add 100 microfarads. So we're gonna add nanofarads, 100 nanofarad capacitor for each of these pins. My bad. NF. Farad is just the unit of capacitance. Hundred nano NF. 100 NF. Now all of these capacitors are of the value 100 nanofarads. And how did I know that it should be 100 nanofarads? I just went to the documentation of STM32. So the manufacturers who made this chip has documented everything, that how much should be these values, how should be your power, like boot loading schematic, how should you connect the memory to this STM32, how are you supposed to connect the different sensors with it. So these pins does not have like much information about what do they do. So a pin of a microcontroller can do a couple of things. So a pin of a microcontroller can do two things mainly. It could either read the voltage, or it could write the voltage. So what do I mean by that? Let's say you connected this pin to any of the device in physical world. Let's say you connect this to a sensor that senses pressure. Let's take for example. If you're gonna apply more pressure onto it, the voltage that the sensor generates is gonna increase. Let's say I put a 100 kg rocket on this sensor. So the value initially was 0, but as soon as I put the weight, it is 100. It is some higher voltage than 0 voltage. Let's say it is 5 volts. So as soon as I put the weight on, the voltage that the sensor produced rose up to 5 volts. Now, if this pin on this microcontroller is a reading pin, then we can read this voltage, and then the manufacturer of this sensor would tell us that how much voltage
let's say X volts represents how much pressure. So they're going to give us a formula that can convert this X voltage that we are reading from our microcontroller here into the pressure. So we can tell that how, like, what amount of weight must be there to generate 5 volts in this case. So this is called reading voltage. So it has a read mode and a write mode, and in the write mode you can let's say you have connected an LED here to this pin. Schematic symbol for LED looks something like this. That is emitting some light, and then this is connected to the ground. So if you program your microcontroller, say that write pin, let's say this is pin 30, pin 30 high. Then what this is going to do is in your software you're going to write this, and then what this is going to do is going to take your voltage of the pin 30 all the way up to 5 volts, and then 5 volt is enough to light up an LED. So your LED is going to light up. So this is how the pins work. So each of these pins could be implemented in different ways. So what happens is we can do simple things like these, but if you have a complicated sensor, then it is not that simple anymore. So there are communication protocols that we have to follow, and then using those we connect our pins, like a couple of pins, to the sensor. So if you're gonna see on an accelerometer, there are 3 main pins. So you have to, or 4 main pins. You have to power your sensor. So for powering, there are 2 pins, and then to communicate back and forth between this microcontroller, that's the STM32, to your sensor, there are other 2 pins. So one of the pins is for clock signal, and the other pin is for the data transfer. So they both have, like every single chip that you see, they have some heart beating inside of them. That is the clock signal, and that synchronizes their processes internally. So if the clock of this STM32 is not going to be synced with the clock of this sensor, then they cannot communicate. That is because it's going to send the data randomly, it's going to take the data randomly. It's not going to be a communication. So to synchronize both of them, there's a clock CLK pin in both of them. So you're going to look up at the documentation of STM32. You'll see which pin is CLK, which pin is clock compatible. Then you will, let's say you figured out that it is pin 11. Then you connected this pin of your sensor to the pin 11 of STM32. And for data transfer, after they are both synced, you can use any of the pins. And then in your program, when you code this, you have to write that initiate serial peripheral interface, initiate SPI, and then you tell your program that the pin 11 is for the clock pin, and this pin 10 is for the data transfer. So we're gonna look into the code in next session. We're gonna do hands-on thing in the next session. This is for just letting you know how communication protocol works. In every single communication protocol that is synchronous, there's a clock line that syncs the clocks, and then there's a data transfer line. Now there are different communication protocols. They implement things internally differently, but the idea is this. Now, this is enough to power your STM32. Now that we have powered it up, we would want to, let's say, light up an LED. To light up an LED, bring this LED here, connect this pin, let's say pin number 41, to this end of the LED, and connect this end of the LED to the ground. Let's copy the ground.
then place it here, connect it all the way. If we apply 5 volts to an LED, your LED is gonna blow up because LED does not have any resistance inside of it, and if your circuit does not have enough resistance, a lot of current is gonna pass through your LED and it's gonna cooked up. It's gonna be cooked. So what you do is you add resistance in the circuit. So let's add a resistor here before connecting it to ground. You can use this delete thing to remove your connections, and then click here, bring your resistor here, rotate this, and then connect it.
Sorry, how do you rotate it again while you're moving? Do you right click as a still or?
I did it but like this. Click on the rotate tool,
Oh.
and then I click on the component that I want to rotate.
Alright.
So we need some more space to bring the resistor here. I'm gonna drag it down, bring it here, rotate this, and now connect these, this to here and this to here. Okay, so we have implemented an LED circuit here. Let's delete all of the rest of the components for now because the time is almost up. It is actually up. I'm gonna delete all of these components for now. I'm gonna save the circuit. There's one more thing that I want to show you before you leave. So there's this button called switch to PCB document. If you're gonna click on this, you will be able to see the actual components. Now you have to place them on this PCB, and then you have to trace the copper paths that I was talking about here. Then you have to draw those to make these connections. Let me demonstrate that real quick. I'm gonna move this group on the PCB. I'm gonna make some space for that. I'm gonna rotate this a little bit. Now you see internally whatever we did here in a schematic is implemented here to help us know where the copper path should go. So for example, like this pin of the STM32 should be connected to this side of this LED. So these lines help us know where do we have to draw the connection. Then use this tool or route manual, and then click on this pad here. You should be able to see that you are drawing. These are the copper paths, and you connect them like this. Then you have to draw this. You have to connect this part of the LED to this resistor. So this is R5. This is the 5th resistor that was in our circuit. And then basically it shows you where do you have to draw the connections, and you just draw them. I'm gonna rotate this capacitor again. And then gonna connect this line to here, this line to here. This line is gonna go all the way up there. This line will also connect here, and this line is gonna connect to here. This terminal will go here. Once you are done with the connections, you can actually send this to a manufacturer and they're gonna print it for you. And then you can solder these components, these small LEDs, on top of that using a soldering paste and a soldering iron. And so here's an interesting problem. I wanna connect this terminal to this, but if I do that, I'm gonna change the circuit. I'm gonna short these two paths. As you can see, like the software does not wanna cross these two paths.
because if you connected these two, you screwed up the circuit. So how can I route this? So this is the last thing that I want to teach you today. You can start routing it here, and then there's a tool called Via. Let me see, where is this on here? Via here, and basically what this does is see if I can find a photo, images. Okay, perfect. So you see, this was one of the copper paths that we were drawing, but we don't want to cross two of them, but we still have to do the routing. So what we can do is we can have multiple floored PCB, and then we can drill a hole. I'll show you. Let's say this is one of our line on the board. We are drawing another line that's coming like this. So we can go down. We can make a hole here. We can go down through the hole, and then as you see here, this is one of the copper paths, and this is the other copper path. If there's a hole and you route like this, you can cross without ever touching the line on the top floor. So you can route underneath that. So you come on this side, you can create another hole, and then you can still connect your component without ever touching that line. So this is called Via. And modern PCBs are like at least four floored PCBs like this one. And Arduino board that we buy, they are also 4-layered. So I'm gonna put this hole right here. So just to show you once again, so I wanted to connect this terminal of this capacitor 4 to this terminal of the capacitor 1. So I'm gonna start routing. I'm gonna drill a hole here. Via tool. I'm gonna drill a hole here. Then I'm gonna change my layer. So you can go in the bottom layer. Flip board. So now I'm at the back of the board. So I can drill. I can keep drawing here. Then I can drill another hole. Oops. Okay, where's the drawing layer? Oh yeah, it's here, bottom. Two, drill hole here. I shouldn't flip the board. Okay, let me try again. It's not allowing me to connect it. That's weird. I can select the bottom layer. So this is now being drawn in the layer below the upper one. So I can cross it without ever touching them, as you can see. So the blue layer is the bottom layer, and the red layer is the top layer. But because this capacitor is placed on top of the PCB, we still have to pierce through once again. We're gonna make a wire hole here. This software is kind of weird, not allowing me to do that. You get the idea though. You just have to connect this without crossing that. So you go in another layer to connect that. This is how you design computers. This is how your MacBook or your Windows computer is designed in real life. So we're gonna make our own computer just like this, implementing some of the communication protocols, logics like these, and that's gonna fly and control our own rocket. I hope you guys like the session, and if you guys have any questions, you can remain seated and let me know.
Otherwise, you're good to go.
Please fill out the form and Discord. The attendance link is given up there.
On Discord?
Discord, yeah. If you're having trouble using the Discord link, just let me know. I'll scan your QR code.
So I'm gonna figure this out, and in my lecture that I'm recording right now, I'm gonna show how feeding This is like my second time using this software. I used to make
Which channel is it on the?
This one.